Hello. This podcast is part two in a two-part series on the fundamentals of scientific investigations. In this podcast, we're going to be looking at what we do after we've collected the data. We're going to learn how to analyze it by creating graphs, linearizing the data, performing linear regression, and developing multivariable equations. And finally, we're going to learn how to communicate our results by supporting claims with evidence. Let's take a look at analyzing data. There's several ways we're going to analyze data, and the first way is creating graphs. We create graphs because it's easier to see trends, and they're necessary to develop the math equations that show the relationships between our independent and dependent variables. Here's an example of a properly formatted graph. So let's break it down. First, it starts with a title, and graphs are labeled as numbered figures. We do not call them graphs, we call them figures. So your first graph is going to be figure 1. Next, it needs to have a descriptive title. My recommendation is whatever the title is for the data table you use to create this graph, you use the same title for the graph. So in this case, we're using the versus format, which is the dependent variable versus the independent variable. Let's take a look at the axes. The dependent variable goes on the y-axis. The independent variable goes on the x-axis. Also, let's look at these titles a little closer. They are titles, so the first letter is capitalized in each word, and we need to include the units. A good rule of thumb is your axes titles should be exactly the same as the column headers from the data table. So for instance, friction force newtons was the column header for the dependent variable on table 1, so it's the y-axis title. And similarly, velocity meters per second squared was the column header for the independent variable on data table 1. So we need to take a look at our data points, and they should be spread out so they cover most of the graph. We do not want them all scrunched in one corner or one half of the table. Notice they are spread out throughout the graph. You can do this on Logger Pro by auto-scaling. Next, we want to draw smooth curves or straight lines through the data, or we don't want to have any curve or line at all. We do not want to draw a straight line from point to point, because if we draw a line, we want it to represent what's going on, and so it needs to be smooth and continuous. So this curve or line may not intersect all the data points and probably won't because of experimental error. So let me just recap when it comes to lines or curves. They need to be a single straight line or a smooth curve that goes through but doesn't necessarily intersect all the data points. Do not draw a series of straight lines from one data point to the next. It is better to have no line or curve than to incorrectly connect the dots with straight lines. Finally, graphs need to be easy to read, so they need to be a decent size. They should cover half the page in portrait orientation or a full page in landscape orientation. Let's move on to our next way of analyzing data, and this is creating linearized test plots. We won't always have to use this. However, sometimes the original graph is not linear, for instance in the previous example. And when that's the case, we do need to linearize the graph. And the reason we need to create a linear graph is that's the way we create a math equation from our data. This summary chart will help us figure out what we need to do to our original data to get a linear graph. It's based on first looking at the graph shape, then understanding the relationship, what modification we need to make, and what the math equation will be that comes from that linearized test plot. So here we have three shapes that are possible to see. Let me just state there are other shapes we can see, but these are the three that we'll see most often in our experiments. We have a curve decreasing from left to right, that relationship would be stated as x increases, y decreases. And just a note here, x refers to the independent variable and y refers to the dependent variable. And our conclusion then would be that the dependent variable is inversely proportional to the independent variable. The next curve is one that is increasing from left to right. Here the description would be the dependent variable is proportional to the square of the independent variable. And our conclusion would be that the dependent variable has a quadratic or second order polynomial relationship with the independent variable. Our last curve is one that's increasing from left to right, but the increase is getting slower. It is concave downward as opposed to the previous curve, which is increasing left to right, but is concave upward. So when we have this concave downward curve, the description is the square of the dependent variable is proportional to the independent variable. And so our conclusion would be that the dependent variable has an inverse square relationship with the independent variable. This is also known as the dependent variable obeys the inverse square law. In the sample we've been looking at, where we had a graph of friction force on the y-axis and velocity on the x-axis, we had a concave upward curve increasing left to right. So that tells us that the friction force is proportional to the square of the velocity. So we can get a straight line, which we call linearized test plot, if we continue to graph friction force on the y-axis, but instead of plotting velocity on the x-axis, we want to plot velocity squared. This will give us a straight line, and then when we come up with our slope and y-intercept from linear regression, our math equation will be the dependent variable is equal to the slope times the independent variable squared plus the y-intercept. So let's take a look at our linearized test plot. We went ahead and plotted velocity squared on the x-axis, kept friction force on the y-axis, and notice now we have a straight line. And we're going to talk about how we use linear regression to get this slope and this y-intercept. Moving on, another tool in analyzing data, as I just mentioned, is linear regression. This will create a math equation from a linear graph, also known as a straight line. We can use LoggerPro's linear fit feature, or on Excel, it's the trendline feature to develop this math equation. It's important to talk about what represents a good fit of the data, because just because these tools on LoggerPro and Excel can draw a straight line through the data doesn't mean that it's a good representation of the data. So if the correlation, which is R, is greater than 0.975, or the correlation squared, which is R squared, is greater than 0.95, then we say the data is a good fit to the straight line. Or another way of saying it, the line or the math equation that we develop from this line is a good representation of the data. Now, just one thing I want to point out, a couple things I want to point out about the correlation. First of all, a perfect correlation would be 1.0, and of course a perfect correlation squared would also be 1.0. These correlations can be negative or positive. I'm talking about the absolute value of the correlation. Now, if you're using LoggerPro, it will give you the correlation R. If you're using Excel's trendline, it'll give you the correlation squared. Once we've run the linear regression and we've determined that it's a good fit to the data, we need to go about writing the equation with the experiment's variables and units. So let's talk about some templates. In math, we learned that the equation for a straight line is y equals mx plus b, where m is the slope and b is the y-intercept. However, y and x are just generic symbols. In science, we're actually measuring specific variables. So this math format, y equals mx plus b, our science template is the dependent variable is equal to the slope of the line times the independent variable plus the value of the y-intercept. So that's the general template we'll be using. And from the linearized test plot, we would plug in our specific values for the slope with units and the y-intercept with units, and we would put in the specific symbols for the dependent variable, friction force, and the symbol for velocity in the independent variable. So it's very important when you're writing equations from your experimental data, do not use the format y equals mx plus b. You need to list the specific dependent and independent variables, either by name or with symbols as I've done here, and you need to list the slope with the appropriate units and the y-intercept with the appropriate units. Lastly, we need to check the 5% rule with the y-intercept. And the 5% rule just tests if the y-intercept should really be 0. Now you may say, well, our linear regression gave us a specific value, but we have to keep in mind that we're working with experimental data, and data has error in it. No matter how good your procedure is, no matter how careful you are in performing your experiment, you're going to have error. And so if the y-intercept is small enough, in other words, if the line is very close to running through the origin, maybe it really should be at the origin. And the reason it's not is because you have experimental error. Well, that's what the 5% rule tests. And it works this way. You take the ratio of the y-intercept to the largest y value from your data table. If that ratio is less than 5%, then the y-intercept is really 0, and we're going to ignore it when we write our equation. So let's apply this 5% rule to our example here. The y-intercept from our linear regression was negative 76.88 kilograms meters per second squared, which is also the same as a Newton. I eliminated the units here because we're just interested in the ratio. Now, we have to put the largest y value in the denominator. The easiest place to get this is from the data table. So I just went back to table 1 and found the largest value, 96,419. When we do the math, it turns out to be negative 0.0008. Now that's the decimal form. That would be 0.08%, clearly less than 5%. Hence, the y-intercept should be 0. And we can simplify our equation to the friction force is equal to 15.07 kilograms per meter times the velocity squared. Let's move on to our last tool for analyzing data, and that's looking at multivariable equations. We have to remember that the linear regression equation only shows how the dependent variable responds to changes in the independent variable. In our example, that was the friction force is equal to 15.07 kilograms per meter times the velocity squared. However, often the dependent variable also responds to changes in the control variables. So we'd like to develop a general equation that shows the dependent variable as a function not just of the independent variable, but as a function of all of these variables. Here's a strategy for starting with your linear regression equation and developing a general equation. And this strategy assumes that the slope is a combination of our control variables. In our example, the slope was 15.07 kilograms per meter. Our control variables were the car mass, which we controlled at 1,500 kilograms, and the curve radius, which we controlled at 100 meters. The first step in this strategy then is to try different math operations with the control variable units. The units, not the numbers, until you get the same units as the slope. So I took our units, kilograms and meters, and I multiplied them, and of course that wasn't equal to kilograms divided by meters. Then I took meters and divided them by kilograms, and that's not equal to kilograms divided by meters. And then I took kilograms divided by meters, and of course that's equal to kilograms divided by meters. And bingo, that's the correct math operation that gets the units to match the units of the slope. Now you may be saying, hey, it was obvious, why didn't you go ahead and just do the kilograms divided by the mass right away? And in this case it was simple and obvious, but sometimes you're going to get more complex relationships, and it truly is just a trial and error process of math operations that get the units to match. Now, step 2, we want to confirm this relationship, and to do this we're going to plug in the numbers for the control variables to see if you get the same numerical value as the slope. So we did for units kilograms divided by meters. Well, that's going to be the 1500 kilograms divided by the 100 meters, and numerically we get 15, and bingo, that matches the slope within experimental error of our graph. So the next step then is to replace the slope in our equation with this combination of control variables to get the general equation. So the friction force is equal to 1500 kilograms divided by 100 meters. That gets us the number of the slope and the units of the slope. So in our general equation, we're going to substitute mass for the 1500 kilograms and radius for the 100 meters. And notice that gives us the equation, the friction force is equal to the mass divided by the radius times the velocity squared. Or you'll more often see it written as mass times velocity squared divided by radius. And that's what we call a general equation. Notice the friction force is written in terms of only variables, not numbers. Now one note here, sometimes the numerical value will be a simple ratio of the slope. In other words, you may have the math operation that gets the units to match the units of the slope, but then when you do this numerical confirmation step, you may find out that the number doesn't match the slope. Rather, it might be half the value of the slope or twice the value of the slope. Sometimes there's some other ratio, but 1/2 or twice are the normal ratios you'll run into. And if that's the case, you simply include the ratio in your general equation. And then remember, the ratio has no units. So this is the strategy for coming up with the general equation. This finishes the section on analyzing data. Now we want to move on to the final step in investigations, which is supporting claims with evidence. Remember, the whole reason we did an investigation was to answer a research question or series of research questions. So we have to recognize that the scientific community requires facts to be proven with data. Opinions or statements without proof are not accepted by the scientific community. So our answer to the RQ, which is called a claim, needs to be proven with our experimental data. There are many ways to write a claim statement or conclusion. Good ones will have the following components. First, it clearly states the relationship between the dependent and independent variables in as much detail as the data will justify. Be as specific as the data will allow you to be. Second, it cites the appropriate tables and figures in your lab report. Third, it gives specific examples of your data that support your claim. Do not, I repeat, do not make the reader go back to the data tables and graphs to find specific examples. Give the specific examples in your claim statement. Let's take a look at what a claim statement would look like for the research question we've been tracking through this podcast. Increasing the car's velocity increases the friction force required to stay on the road. The data in Table 1 shows that a car traveling at 5 meters per second only needs 379 newtons of friction force to stay on the road, whereas doubling the car's velocity to 10 meters per second requires the friction force to be almost quadrupled to 1,511 newtons. The linearized test plot and regression analysis from Figure 2 shows that the friction force is proportional to the car's velocity squared. That is, the force of friction is equal to 15.07 kilograms per meter times the velocity squared. Notice this statement meets all three requirements of supporting a claim with evidence. Well, this wraps up our two-part series on scientific investigations. I hope this helped and have a good day.